The next thing I would like to illustrate is how peak labels can be used to quantify the sample. So let's have a look at the as received survey measurement. Here we have a set of photoemission peaks, and they give an impression of the amount of oxygen, carbon, and the titanium and the nickel. Not much nickel, more titanium, carbon, oxygen. Yes, these are significant, but how significant? And we only know this if we integrate the signal above the background, adjust the signal for the relative sensitivity, so the photoemission cross-section, and various other corrections such as escape depth and transmission. These all contribute to producing an amount of oxygen, carbon and titanium. I won't bother with the nickel because there's not much of it and it isn't necessary for this demonstration. I just want to show how labelling these peaks here will allow a quantification table to be produced from a survey measurement with an indication of the amount of substance as measured by XPS. Now we have to be very careful here that we don't draw too many conclusions from this, because this is clearly a complex sample and it has in-depth distribution, because we have a contamination layer, a native oxide layer and a substrate that is an alloy. So this is not very conducive to using quantification as a concrete estimate of the elemental composition of the sample. That is reserved for more well characterized materials such as polymers, or anything that has a bulk material with a surface composition is comparable to the bulk. This one definitely is not. Nevertheless, what I'm going to do now is use the annotation dialog window and the peak labels and the quantification parameters dialog window and the regions property page. And the button that I'm going to use on the regions property page to create regions, and this will allow me to correlate relative sensitivity with specific photoemission peaks and therefore calculate the relative amounts of these three elements that I'm considering. This button here, create from labels, is the thing that will correlate the creation of these regions with the information that I supply via these peak labels and the element library. So the element library is the starting point. I need to extract from the element library RSFs. I can identify the RSFs with photoemission peaks by identifying the peak labels for the ones that I'm interested in. I'm interested in the oxygen 1s. I'm interested in the carbon 1s, holding the control key down, and titanium 2p. I could have chosen a different titanium RSF by selecting a different peak label. I could have labelled the titanium 2p using the titanium 2p 3/2 peak within the doublet. I'm not. I'm going to use the total RSF because I'm selecting the titanium 2p. And now that I have my selection made, I can create the labels. We just get rid of the quantification dialog window so we can see the labels being created. And unfortunately that demonstrated something, that when it updated the display it also removed the selection, because each time you make a modification to the display or another dialog window, that you may negate or invalidate the selection that you've previously made. So to prevent spurious labels being created, it then goes back to square one, and I can then go through and select once again my three peak labels that I'm going to use for quantification and press apply. And there they are. So we've now created the peak labels, and they do appear on the annotation history. So here we have the history showing the three labels that are created. If I wanted to move them, I could have used these boxes here to adjust if they happen not to align with the peaks, and that is possible. So let's now dispense with the annotation. We don't need the element library, so there's no confusion here between how these regions are created. They are created from the annotation, not from what is selected on the element library. And then when I bring up the quantification parameters dialog window and I have labels, annotation labels on these peaks, I can then apply the create from labels button, and this will create 3 regions, and the regions, because I've created the labels from the element library, will bring in the appropriate relative sensitivity factors and label the regions accordingly, so I can then quantify in terms of the different amounts of material in terms of oxygen, carbon and titanium. But simply because they look plausible when they're in a full display doesn't mean to say that these regions, when we zoom in, actually are perfect. So what we need to do is load the regions onto the zoom list. I did that by pressing the reset button and then using the zoom out, and that zoom out allows me to inspect each one of these regions, and I can see straight away that I needed to adjust the titanium 2P. What had happened was that because there's a minimum here, it had chosen the maximum peak here, the more intense part of the doublet peak, and that would be the 3/2 peak. So I could have chosen a different relative sensitivity factor. I could have used the titanium 2P 3/2 peak to quantify. It would have brought in a different RSF that would have matched what was achieved when the region was created. I didn't want to do that. I want to include all the signal from titanium 2P, so I've had to make an adjustment. If I now click the out again, zoom out again, I can then just have a look-see at the carbon, and here we see the oxygen. So I've just made a couple of adjustments to improve the relationship between the background and the photo emission peaks. So this area here will be integrated, it'll be scaled by the relative sensitivity factor, and the same will be done for each one of these regions. We can now put up a quantification table based on regions over the data. Let's zoom out and we'll press apply. The annotation table that is created from regions will be the annotation table based on the regions on the display data in the active tile. So the survey measurement, this is the only source for the quantification in this instance. When we apply the regions button, we get a table, and let me just move that table so I can see it better away from the data itself, and it gives us an estimate for the amount of oxygen, carbon and titanium based on what XPS can actually measure. So oxygen and carbon, you can say there's about the same amount within the sampling depth. Well, not altogether true, because this has an in-depth distribution. If the oxygen is below the carbon or the carbon is below the oxygen, then these numbers would alter, and therefore you have to be aware that quantification by XPS, you have to have a good understanding of how the sample composition and its in-depth distribution exists on the sample surface before, when I say the sample surface, I mean the sampling depth of XPS. In the case of aluminium, X-rays, it's about 10 nanometers at best. So we are literally looking at the outermost layers of the sample, and as a result of that, we do not see the alloy hardly at all. In fact, what we're seeing is mostly a relationship between titanium and oxygen and adventitious material. So it just so happens that these are equal-ish, they're equal, but we should not draw too many conclusions about the quantification, because we do have a complex sample here.